Okay, that's working now. Yeah, we're fine. All right, guys. Actually, let's take the attendance. Let's just see. Ratimi. Yeah. As I do have today, and Alex, are you there yet? No Aziz? No. David? Yeah. Sabrina? Yeah. Amy? The girl who likes to go, huh? No. Not him. Again?
Oh, okay.
Oh.
Huh? It's okay, just process.
I hope she comments on my video. I hope she comments on my video. Right, Nikita here. Ray, yes. Barack. Priscilla. Patrick. Is he sick or something? No? Joshua? Vanessa?
No.
Okay. Umar? Diana? Hussein? Yeah. Dasha? Ishpreet? And Mo? Okay, not too bad. Right, now what we're having a look at in the first class is what's called the binomial distribution. Now you definitely will need your calculator for this if you want to take it out now. Guys, you will need your calculator for sure for these problems, so you can take it out now. Have you got it yet? No. Now, binomial distribution, another name for it is Bernoulli, but I think we call it binomial here. The bi here, meaning two. What we're going to, two nomials, yeah. What we're looking at here is what's called trials. These are probabilities where one of two things could happen. An event could happen or could not happen. The coin could land heads or land tails. Okay, it's important that it's only referring to two possible outcomes. And the idea is you'll have a trial of, say, n. So that means there are, maybe for example, n coins are flipped, something like this. You have n situations, and each situation could either end in success or failure, heads or tails, up or down. Okay. So for example, maybe in this picture it's 6 trials. You flip 6 coins, and you would like to know what's the probability that maybe 2 of them land up heads and maybe 4 of them end up as tails. But you don't care which 2. Okay, you just care that there were 2, but not which 2. Okay. So is this kind of more like a combination or a permutation, where you don't care about the order? It's more like a combination, isn't it? You don't care which ones landed up head. You just want to know what's the probability that there's 2. So there is actually a nice, neat little formula that lets you calculate this. Before we give you the formula, I'll just give you some terms. So P here is the probability of success, or heads, or whatever it is in the question. So I'll just write here the probability of the event, which is usually something like a success, or heads, or yes, or whatever. Okay. Q, which is the same thing as 1 minus P, What do you think that would represent? 1 minus p.
The event of-
Yeah, probability of no event.
What's Q?
Just means probability not happening. 1 minus p, that's all it means. It's just short for 1 minus p. That's all. You can actually replace q with 1 minus p if you prefer. N is the number of attempts, or the number of trials. And or x actually, I'll use x because I think x is in the formula book. X is the number of events, the number of successes that you want to calculate for. So the formula is the probability of x events in n trials equals ncx times p power x times q power n minus x. Now I think the formula book maybe writes q, or maybe it actually writes 1 minus p. I'm not sure. I'd have to open it up, but I'll write it as q just to make it a little shorter. N minus x, like that. So for example, this one here, what would be the probability of getting the two coins to land up heads? Well, that would be 6c2 times p, and what's p?
12. No.
Wait, how many the number of events is 2?
1, 3.
Oh, in this question here, I'm wanting 2 heads from 6 coins. 1 over 2.
What?
Flip a coin.
Oh, okay, 1 over 2. Yeah.
I did
Yeah,
6
yeah.
times 2. Oh.
No, it just P is for one single event in question. Okay, what power? X, and what's X here? 2. And then Q? Half as well. And what power? 4. Now there's actually an easy way to remember what you're doing here. Have a look. Look. It's the probability of a single success to the power of how many successes you want, times the probability of a single failure to the power of how many failures you want. So the only thing that you have to be careful about is this guy up here, 6c2. It's the total number of trials and the total number of successes. By the way, if you were to replace the 2 with a 4, you get the same answer. So you can use the number of successes or the number of failures. It's kind of common to use the number of successes down here. Okay. So practice with your calculator. Can you tell me what this example would be? Yeah, it should be small enough. So what's that as a percentage?
23.4.
23.4, is it? Is that okay? Yeah. Yeah. Can I scroll down?
No. 1 second.
Not yet? Okay. You got that? Yeah. Nikita?
So the first number is a probability of single event
Yeah.
To the power of
How many?
yeah.
Yeah.
it's a
And then
simple
failure,
of,
how many? Yeah.
just actually I put the pictures.
Yeah, can I scroll down?
Yeah.
Yeah. So let's have a look at a more complicated example, but I'll start it off easy enough. So you're rolling a die here, and we'll say that success is if you get a 6, we'll say, and failure is not a 6. Now the reason I have to do this is because it's binomial. I'm only looking at 2 possibilities. What's the P here?
P.
1 over 6.
1 over 6. And the Q?
5 over 6.
5 over 6. And let's say I roll the die a total of 10 times, and I'll give you an easy enough one to just to warm up here. Let's say the probability of, well, let's just say the probability of 5 successes. Actually, I'll just use a little tick for success. 5 successes. What would that be?
From where did you get the P is equal to 1 over 6 and the Q is equal to 1 over 6?
You know what a die is?
Yeah,
How many sides?
6.
6. So what's the chance of getting the number 6 if you roll it?
6.
6? No.
Oh no, it's
1 over 6.
Yeah. You need to get 6.
Yeah, get 6 to win.
There's only 1.
Get 6 to win, yeah.
Yeah.
Only one of the sides is a 6.
And 5 sides it's not 6.
Correct, yes. Yeah, and those numbers are 1, 2, 3, 4, 5.
Oh.
Yeah. You don't gamble, Hazel?
No. I just play Monopoly.
Oh, well then you have dice in Monopoly, don't you? Right. Okay, what's the answer for this one?
1.3? I don't know.
1.3? No.
Okay.
It has to be less than 1, of course.
No, 1.3%.
Oh, 1.3%, thank you, okay. So let's just put it as a decimal this time. 0.01.
Wait, 1.3? Is it correct? I don't know.
Yeah, it should be pretty small because, yeah, it should be pretty small because is it likely that you'll get a 6? No, it's not really likely. So getting 5 of them would seem quite unlikely, wouldn't it? Yeah. Okay, B now. Let's say I ask you for 0 or 1 success. Now, the or is important here. How does that change things slightly? Yeah, you have to do 2 calculations and add the results together. So it would be 6C0 oh, sorry. I forgot. We wrote it 10 times, didn't we? Plus 10C1 1 and 5, 6 power 9. Okay, so I think this should be a big enough number. I mean, if I roll a die 10 times, I kind of do expect to get a 6, maybe once or maybe not at all.
4.3.
Yeah, it's still pretty small actually, isn't it? What did you say, 0.
Wait, I lost it. Oh. Okay. It's lost somehow.
Do you have answers, Carew?
Is it?
What's wrong?
Now I got one.
Got your calculator?
Yeah.
Come on, guys.
I was doing it, but I got confused. Yeah, I was right.
0.0485 then.
What does it mean? 0 or 1, right?
Wait.
Zero.
No.
Oh, I'm asking what is the probability that you get no successes or one success? Oh, sorry, it's actually much higher, 0.485. Yeah, so that means it's nearly 50% likely that this would happen, that you get 0 or 1, 6 showing up. Yeah? C now. Okay. Now let's make it a little bit harder. You really have to think about, well, not really have to think about this, but suppose I say 2, 3, 4, or, well, basically 2 or more successes.
So it's just minus by 1?
Yeah, that's it. We can use the previous answer here to help us.
0.515?
Yeah. So suppose I ask you, what's the probability of getting in this situation? And then I ask you, what's the probability of not getting this situation? Well, it's 1 minus. So all you need to understand is that this is the not. It's the opposite of this. Which it is. If you get 0 or 1 success, the opposite of getting 0 or 1 is every other possibility. 2, 3, 4, 5, 6, 7, 8, 9, 10 successes. Yeah? Now it's important that you have that in your head. Okay, because when we do the next lesson, I'll note it'll fall out of some of your heads. It will. You can already feel it leaving you. D. Okay. The probability of at least 1 success. So that's a simple way of saying at least 1 success means 1 success or 2 or 3 or 4. In other words, you get at least a 6 showing up once.
So 1 minus 0.
So
Yeah.
to calculate, we need 1 minus 0.
Yeah,
1
She's
minus
right.
0.
1 minus, and what's the opposite situation though?
When we have 0.
Yeah. The trick here is to realize at least 1 success is the same as saying 1 or more. And you can do the not trick here. You can say this is equal to 1 minus the probability of not 1 or more. Now watch, I'll just write that on the side. If you have A, you can say that's equal to 1 minus the probability of not A. Are we all agreed with that, right? Yes? Yeah. So that's all I've done here. I've said at least 1 success means, it means the same thing as 1 or more, doesn't it?
Yeah.
And using my not rule, I can say probability of 1 or more is the same as 1 minus the probability of not 1 or more. Now what is the meaning of not 1 or more?
0.
Yeah, that can only mean 0 successes. So that would be 1 minus 10C 0, 1 over 6, 0, 5 over 6, 10. Okay, so what's that one now?
0.838.
0 point what?
838.
8385. So then it'd be 9 then.
I got 0.8384
Then it would be 8. Yeah. Okay. Now that's an important example because they like this one in the exam. They like doing this in the exam for the binomial question because it makes the student do a little bit extra than the previous examples, okay? So please make sure you have this one carefully taken down in your notebook. It's a good exam question. Okay, can I continue?
Yep.
Yeah.
Is these all in one answer?
What do you mean?
Yes.
Like,
Yes.
Oh yeah, like this is all for part D. Now, there are two more types of binomial problems I want to do in this class. So, really, the examples A, B, and C, they're not really meaningful examples because all you're doing in the three of them is just using the formula. It's not until we get to part D where we actually use the formula in, a way that's difficult enough for the exam. Okay. There are two more types of problems that they like in the exam. The first type of the two I'm going to do is a very common one. I call it a sort of a nested problem because it has a small problem and then that's inside of a bigger problem. So we'll do an example. I think the example that they had, it might be something like a biology example where you have some kind of experiment and there's 6 samples in it, I think it was. And I can't remember the story, that's not important, but something reacts and a colour changes. And we'll keep it simple. We say a success means the colour changes green, and then failure means it stays red or something like that. We'll keep it simple. So the n here is 6. The p was given in the question. I'll make up a number. We'll just say it's 1 over 4, something like this.
it should be 1 over 6.
No.
Yeah, it's 1.
No.
It's 1 like
no.
success and 6. No, it should be 1 over 5.
It should be.
No. If I have 6 people,
Yeah.
how likely is it the first one will be male?
1 over 2. 1 over 2.
1 over 2. 1 over 2.
And here's like just made up experiments.
Oh.
Yeah.
Like have probability 0.68.
So,
Yeah.
so there are 4 chances to, 4 different colors.
Synergy.
Hang on.
Because 5 are like.
Hang on.
Wait, what?
Hang on. You guys are getting stupider. Listen, okay? You have 6 containers, 6 vials, whatever, 6 test tubes, okay? You put a solution in each test tube, and they're all red. Then you wait a little bit, and maybe, by chance, some of them, one of them, all of them, some of them will change to green. How likely? I'm telling you how likely. It's a 1 in 4 chance that it will spontaneously change to green.
So, okay, just given.
Yes, I am giving you this information. Okay?
So it's not.
Yeah, you got it? You got it? Okay. So, let's say that we consider the experiment a success if none of the vials turn green, if they all stay red. Okay? So I want to know the probability that the experiment was a success, that everything worked. And that is the same as saying the probability that you have 6 red, basically.
Should be 6 green because green is the correct one.
Yeah, well, you don't know what green represents. Green could represent having the coronavirus, and then it would not be a success, would it? You know? You have no idea what green here means. Green could be like, coronavirus or something. Okay, so take out your calculator and give me the probability of getting a success by having 6 red results here. And remember, the 1 in 4 is for getting a green.
Are we supposed to use the formula?
Yes. So you should have, now there is 2 ways of thinking about this. You can think about this as getting 6 reds or as getting 0 greens. So it doesn't actually matter. You can have 6C0 or 6C6. It doesn't matter. It's the same number. So I'll just say greens. I want 0 greens times the probability of a green, and I want 0 of them, times the probability of a not green, and I want 6 of them. So what is the probability here? 178, like that.
So if I use the C6,
Yeah, I'll just so you can see the other way to do this, or is you can say 6C6, 6 reds. A red is 3 over 4, and you want 6 of them. And then a not red is 1 over 4, and you want none of them. So you can write it either way. It depends on which point of view you want to take, but it's the same number answer in the end, so it doesn't matter. And what did we say this was? 0.178. Now, there's nothing new in this question so far. This is just using the formula. The new part comes next. I call this, I think I said this, I call this a nested problem, because then what they would do next is they would say this here experiment is done in batches of 4. So maybe you have your lab table here, and the experiment is done by 4 students, for example, like this. For example. So each of these is one of these guys. And the question I now ask is, what is the probability that it worked for 2 students? So 2 of the students had success and 2 of the students had failure. Now, can you see why I'm saying that this is what we call a nested problem? Because this smaller problem is inside of this bigger one. But it actually doesn't make it as complicated as it sounds. All you need from the previous answer is this. So, see if you can use the binomial formula to get it here. I want 2 experimental successes and 2 failures.
so it's 4.
So yes, it'll start off with 4C2,
And then use that one as the P.
and this we said is a success. It worked. So it'd be 0.178 power.
2. Right.
And then here, 1 minus 0.178.
Also to the power of 2.
2. So actually it doesn't matter which way around
But
it
if
is.
it would be 3 students successful. So it will
Yeah,
be
this would be 3-1, yeah. Okay, so what do we get here? 0.128. I see this in the exam frequently. They put a problem inside of a larger problem. So the problems are nested. But you realize it actually, I mean, it's the same. It's just all that's changed are the numbers, but it's still the same formula. So again, you need to write this down carefully, as this is another example here. Now, the previous example I did with, what was it I did previously? The at least one? The dice, yeah. That would be a section A question, whereas this one now is more of a section B question because it has multiple parts in it. So you would see something like this in section B. Okay. Can I scroll down? No. The last type of example is not really common in the exam, but it's another possibility. I call these problems end on success. So it's usually something like, oh, people are flipping a coin and you want maybe 5 successes, but the last flip has to be a success, or something like this. I'll give you an example here. Okay. Can I scroll down? Yeah. So Example might be someone is playing basketball, and the probability, if they take a free shot, that they score, we'll just say it's, we'll give them a 50-50 chance. No, that's too nice. We'll give them a 1 in 3 chance of scoring if they take a shot at it, okay? So, let's say they took in total 5 throws. Okay, I would like them to score 3 times, but the last score was on the last throw. So they score 3 times. However, I do care slightly about the order now. I want their 3rd success to happen on their last throw of the basketball. Yeah. If I didn't say this part here, then the answer would just be 5c3, 1 over 3 power 3, isn't it? Yeah, and then 2 over 3 power 2. If I didn't add that piece in, but I did, so it changed it a little bit.
So it's 5c2?
Yeah, we need to picture this now as a little bit of visualization. 1, 2, 3, 4, 5. They're 5 attempts. You want the last one to be a success. But you do not care what happens here, except that they score twice.
Or 2.
Yeah, so maybe, you know, they could have something like this, for example. So, what you have relating these 2 parts is an and. You want this, no, and. Times. You want this, and then you want this. So let's look at the first half of the story. They want 2 successes in 4 tries. What would that be? 4c2 times 1 over 3, 2. 2 over 3, 2. And then
Multiply by
1 over 3. Okay? So, although it seems quite difficult at the start, once you visualize it correctly, it's actually not that hard. So, what do we get here? 0.066, is it?
Wait, nope, something wrong.
No? Is it 0.
Wait.
0.099.
Yeah.
99, is it? Yeah.
Could you please
Zoom out.
repeat about how we are getting 1 over 3? This is the last one. As a condition.
Ah. 1 single throw of the basket, what's their chance of success? Well, it's given at the very start. So?
We just isn't. We just know the first one. Thank you.
Okay, that's another exam style question, so please take that down carefully. Okay, one last thing just to show you on this. Do you have that? Yeah? So, you could work out, I'm going to give you 2 more formulas, but you could actually work out the first one already. Let's take the example of a coin. I flip a coin. What's the probability that I would land on heads? 1 over 2. If I flip the coin 100 times, how many heads do I expect? 50. Now, in your head, what formula, what did you multiply to get that? A half times 100. Yeah. So, let's just keep it general for the moment. Let's suppose we have n trials, and P is the probability for success as normal. What is the expected value for the number of successes? Now, you just did it a moment ago with the coin. Yeah. We think it should be n times P. So if it's a coin and you flip it 100 times, you expect on average in the long run how many successes? 50. Will it always be 50? Of course not. No, just this is an expectation. And what also goes with expectation? The variance. Now there's no way that you'll guess this formula, so I'll just give it to you, but it's actually not that different. It's NPQ. Okay, so it's only slightly different. Yeah, so actually, again, if we go with the example of the coin, 100 flips, and it's a half likely, 50, and then this would be 25. Yeah. What does it mean, and if the variance is big? What does it mean? It means you get lots of fluctuation when you repeat this situation.
If we have bigger amount of trial, we have smaller fluctuation rate.
Say again, if you have...
If we have bigger numbers of trials,
Yeah.
we have smaller
Fluctuations?
Yeah.
No, like even if you take a small example, say you flip a coin 10 times, how many times do you expect it to land heads? 5. The variation isn't that big. It can only be 0 or be 10. But if you flip it 100 times, you could get 50 heads, but because you're flipping it more, you've actually opened the window wider for the number of possibilities. Yeah. Yeah. Yeah? Okay. Let's see. You can try these for a few minutes. Let me tell you which ones would be good to try. Yeah, there are a few to try. There you go. Hazel, did you write those questions down? I want the three of you working now, come on.